Hey everyone, the objectives for this video are the following. Describe why atoms tend to ionize, because when they ionize, we could then describe what happens when ions of opposite charge chemically combine. We're then going to compose chemical formulas for ionic compounds and hopefully get to draw electron dot diagrams for ionic compounds. Those are our Lewis dot structures. Alright, let's begin. We want to describe why atoms tend to ionize in the first place. Let's re-examine this rule called the octet rule. And remember, the octet rule has us thinking that to achieve a stable valence shell, remember a valence shell is the outermost shell of an atom. So to achieve a stable valence shell, atoms will either gain or lose electrons. Now it's called the octet rule. Octet relates to the number 8 because in almost all the atoms available, the outermost shell can handle 8. Now this is not true if the outermost shell is the first shell. So I'm drawing here the nucleus. Here's the first shell of an atom, the second shell. If we are talking about this first shell only, it can achieve its stability with only 2 electrons. If it goes beyond that, it must be 8. So let's explore this concept of the octet rule by looking at a few group 1 metals and perhaps a group 2 metal. But let's first start with lithium. Lithium has an electron configuration of 2, 1. Now you have to consider which is easier to achieve stability in the outermost shell, gaining 7 or losing the 1. It is far easier to lose the 1 than to gain 7. So lithium will lose this 1 outer electron. This first shell is now the valence shell. It is stable. And lithium now has a +1 charge because it was neutral, but it lost now an electron. So this +1 that I'm circling suggests that that is in fact what occurred. Sodium. Sodium's electron configuration when it is neutral is 2, 8, 1. Is it easier to gain 7 or lose 1? Far easier to lose the 1. It now has an electron configuration of 2, 8. And it becomes a +1 ion called a cation. Alright, now let's also take a look at magnesium, seeing that it's on the screen. I'll change colors so that we can follow the work for magnesium. Magnesium is 2, 8, 2. Is it easier to gain 6 electrons or lose 2? Far easier to lose the 2. Now that it lost 2 electrons, magnesium has a +2 charge. Next slide, we'll take a look at what will happen to nonmetals when they ionize. Alright, so now on this side of the periodic table we have our nonmetals. We have group 16, group 17, group 18. Let's see what happens when they tend to ionize. Let's first take a look at neon. Neon has an electron configuration of 2-8. 2-8. The outermost electron is already full of 8 electrons. It is stable. It is happy. It will tend not to react. In fact, that is why right here you see a 0, because it will not tend to ionize. Argon, the same deal. So let's instead focus on fluorine, which has a 2-7 electron configuration. Is it easier to lose the 7 or gain 1? Far easier to gain the 1. It then acquires an electron configuration of 2-8. Now because it gained an electron, it now has a -1 charge, and we call that an anion. Alright, let's take a look at oxygen at 2-6. 2-6. Easier to lose 6 or gain 2? Of course, gain 2. Alright, so now it has an electron configuration of 2-8. It gained 2 electrons. It was first neutral. Now it has a -2 charge. We're now going to go on to our next objective. We need to discuss if we have 2 ions of opposite charges together, what will happen? So now let's describe what happens when ions of opposite charge chemically combine. So we had an example of sodium. And sodium had an electron configuration of 2, what was that? 2, 8, 1. And we had fluorine, which was 2, there it is, 2, 7. Well, let's think about this. Consider it a puzzle. This guy wants to lose an electron. This guy wants to gain an electron. What might happen? Exactly that. The sodium loses an electron, the fluorine takes it. So they will chemically combine and become this new substance called sodium fluoride. Now this is easy to understand. This is a 1-to-1 ratio. This has 1 to give off, this has 1 to take. But it doesn't always work that way. But you need to always consider that if something needs to give up electrons, there might be something that can take them. All right, and we call this an ionic bond because as this becomes an ion, as this becomes an ion, they actually achieve a, let's call it a magnetic force of attraction because the sodium became positive while the fluorine became negative. They are now sticking together. They need one another. We had a transfer of electrons. Now this slide is nice too. It's showing pretty much the same thing. We have sodium with its electron configuration of 2, 8, 1. And in this case, it's chlorine with its electron configuration of 2, 8, 7. Well, what will happen? Well, the outermost electron of the sodium is transferred to the outermost shell of chlorine, stabilizing it. So we ended up getting at first 2, 8, 1. This was 2, 8, 7. This is now 2, 8, while this is 2, 8, 8. They're both stable, and because they need each other, they chemically combine, and this is called sodium chloride, the same salt you put on your French fries. On the next slide, we'll see a situation where it's not a 1-to-1 ratio. So let's move to that one and dissect it so that you understand it best. All right, let's look carefully at this example here. Here we have in the center magnesium. It has an electron configuration of 2 x's in the first shell, 8 x's in the second shell, and 2 x's in its valence shell. Now we also have chlorine present. Chlorine is a 2, 8, 7. Over here, another chlorine. It is a 2, 8, 7. Now each chlorine would like to have 1 electron. And what's so very nice is magnesium has 2 to give. It could actually give 1 electron to one of the chlorines and 1 electron to the other. And then what does that look like? Well, it looks like this. Now if you notice, for simplicity, sometimes the electrons can be drawn as dots and sometimes X's. I don't care, you could even put triangles. What they're trying to do here is show you the source of the electrons. So for instance, the electrons that were marked as X originally came from magnesium, while the electrons marked as a dot came from the chlorine. So pause if you need to, really take a close look at this example. Hi everyone, now we're going to compose chemical formulas from the ionic compounds. And I used the periodic table to pull out these elements. And right now we are going to put down what is the ion each of these tends to become. Sodium positioned in group 1, which is right here, tends to become a +1 ion. The plus without a number indicates it is +1, so sodium +1. Calcium is in group 2 right here. It tends to like to become a 2+, and so 2+. Now taking a look at fluorine and sulfur. Fluorine likes to become a 1- and sulfur a 2-. So let's go ahead and put those in. Get this out of the way now. So what will happen? So I said fluorine was a 1-, 1-, 1-. while sulfur is a 2 minus and a 2 minus. So let's take a closer look at when sodium and fluorine combine. Sodium gives up one electron, fluorine likes to give one away, so we just call that sodium fluoride. It's a 1-to-1 ratio. The next one is a little trickier. Sodium likes to give away one, but sulfur wants two. So we will need to provide two sodiums for one sulfur. Now there's a nice way of doing this. There is a trick, and it's called the crisscross method. What you do is you take a look at the number you would have here, called the oxidation state. Okay? And you drag it down to here. You take this number and you drag it down to here. So let's put those numbers in. This would end up being a, grab the pen, a 2. This would end up being a 1, but we never write the 1. So let's get rid of that. So what would be the formula for this scenario? Na2S. Now you should pause at this moment, see if you could do the next two. But I'm going to keep on going. I'm expecting that you paused it. Now here we have calcium and fluorine. Calcium could give away 2 electrons. Fluorine can only take 1. So how many fluorines will we need to take both of those electrons? If we do the crisscross method, well, let's write in the calcium and the fluorine. The 1 from the fluorine drops down to under the calcium, which would be this position. So we don't need to write it. A 1 is implied if it's not there. And the 2 from here drops down to that position. So the formula would be CaF2. Now conversely, what about this last one? Well, put in the calcium and the sulfur, and you would think that if you drop the numbers down from the corners, it would be Ca2S2. Now there's a trick to this. We simplify it. This is a 2-to-2 ratio, which then could be simplified to be a 1-to-1 ratio. So the true answer is CaS. So this brings us to draw electron dot diagrams for ionic substances. We already know what they look like for individual ions, but what will they look like when they combine to become an ionic compound? Now forgive the resolution. Here is the dot diagram for potassium. Potassium has 1 valence electron, so it only has 1 dot, while chlorine has 7 valence electrons. So we do know that the valence electron from potassium is going to move over to join the valence electrons of chlorine to stabilize both at the same time. And what does that look like when that happens? Well, we then draw it like this. Note that the potassium, which acquired a positive charge when it lost this electron, is now depicted as being a positive. Now remember that this takes on the term a cation. Now chlorine. Chlorine now has brackets around it. You do see the electron that it stole from potassium, and it is acquiring a negative charge. It has 1 extra electron. Remember, it was neutral. It now has an extra electron, which is negatively charged. It's a -1, and this is called an anion, a negative ion. Here's a quick example of calcium. Calcium has 2 valence electrons, and oxygen needs 2 more valence electrons. The calcium acquires a +2 charge. Notice its dots are gone. Where are they? They're right here. Here and here. And oxygen now has a -2 charge because of the extra 2 electrons. And last, this is an example of when 2 magnesiums join with 1 chlorine, how the electrons not only move, but what the electron dot structure, electron dot diagram should look like.